People at home, can you guys see that okay? That's a little better. I have a hard time hearing you too. 8.2, we're not going to. We're just going to skip that because of time. So 8.7, hopefully by the end of the week. I think Wednesday or Thursday. So I think the 8.1a homework assignment is due tomorrow. And then 8.1b I think is due Wednesday. And then we're starting, or maybe it's due Thursday. I can't remember which day it's due. But I want us to be done our curriculum before spring break. And maybe give you guys like a small quiz on these two sections. And then going into spring break, I want us to be doing AP review. AP? The spring break, I think, is in 2 weeks. So we got this week, next week, and then spring break, right? Yeah.
Our test is in 6 weeks, guys.
6 weeks to the AP test?
Yeah.
Nice. What's the date?
Whatever that Monday
Wow.
is. Whatever that Monday is.
Well, last year's was late because of COVID. I gave like 3 different testing windows for us to choose from, and we chose the latest window that was available for in-person testing for the first test. So last year was like
May 9th.
we're not doing that this year. Yeah, stuff in italics for me to read, absorb, maybe take like abbreviated notes on if you feel like it. Yeah, basically. So this is what you should really have. The rest. Oh, also, plus C, except for example 2. Oh, example 6 is for my blocks 1 and 3.
Would Liz Darkowitz please take room 3 for coverage? Liz Darkowitz, please take room 3 for coverage.
All right. Does anybody need more time with the notes? If you're wondering about example 1, we did that on Friday together on the whiteboards. And instead of doing whiteboards, I think it'll just be discuss as we work through. So you said she'll email me. I have to email her. Anybody need more time with the notes? We're good? All right. Oh, your chapter 7 tests. Should they go in the 3rd quarter or the 4th quarter?
The 4th quarter. No. I want to see my grade first. Yeah, are you going to give us back our stuff? Yeah.
I'm hoping to. I was hoping to give it back today, but then Arif's not here.
Like, I'm not going to tell them the answer. Tell them wrong. Is everyone finished the test, or are there still people who need to pass?
Armand's got to get more time today because he didn't get to finish last week his physics, and Arif is in the same boat.
We decide tomorrow when we get the test.
Yeah, that's fine. Yeah, we'll decide that tomorrow. We'll punt that discussion. All right, example 2. Sam, would you please turn on the backlight switch? Or Bethlehem? Or somebody? I don't care who. Thank you. Oh, that's nice. So we got the integral from 0 to 1 of x plus 3 over 4 minus square root of 4 minus x squared. What might be your first kind of inclination of something to do here? Use sub. And that's reasonable because the derivative of the inside does kind of fit with the x plus 3 up top. So you could try saying, let's try u sub, have u equal 4 minus x squared. And then what's du going to be? Negative 2x dx. And then what do you see is missing from our du versus dx equation that you have here. It's plus 3 business. So we have a whole extra constant. Can we just add in a constant there? No. So what we do is we separate this out and say, oh, we need to deal with this plus 3 kind of on its own. So we're going to separate this into 2 fractions. The x part works pretty nicely with our du dx relationship.
Is the one
The 3 doesn't.
trig one?
Say again?
Is the one with trig 3 a trig one?
Yeah. So then we're going to have, all right, x over the square root of 4 minus x squared dx. And you're using this stuff over here. But then we've got the integral also of 3 over the square root of 4 minus x squared dx. And this is not going to be that u substitution. What do we need to do here instead? Probably an inverse trig, I'm guessing arcsine. Because if you look at the denominator, we've got the square root of a constant minus an x thing squared. So that's cool for arcsine. And for this guy, if we say, hey, arcsine pattern, what's in the u slot for our arcsine? X. And then what's du? Dx. Okay, that works out because for arcsine we want du over the square root of a squared minus u squared. Well, basically we have that. We just have an extra 3, but that's a constant multiplier. We can pull it out. So we can think of this as 3 times the integral of dx over the square root of 4 minus x squared. And then what's our a value? 2. So just be careful, a is 2, not 4. So this second integral, once you've broken this up, we have a straight u sub, and then we have an arcsine situation. So one of our tricks for doing integration is break apart a fraction like this. So then let's just kind of finish off this second integral. So not with that. What's this going to be? Say 3, and then arcsine of, what is it? X over 2. And arcsine is the one inverse trig that doesn't do 1 over a out front. So it's just whatever constant multiplier times the trig function, and then you just have x over a, or u over a inside. And then going from 0 to 1. Yes, sir. Arc tangent is if there's no square root, and it's like u squared plus a squared, and then arc secant.
That one's the square root.
Yeah, arc secant is tougher,
Arc is absolute value.
is absolute value here, and that pattern is when you have u times the square root of this thing reversed, u squared minus a squared. So then back over here, what do we need to multiply by to fit the pattern to our u substitution? -2, so we'll multiply by -2 and -1/2 on the outside. So then we have -1/2 times the integral, and this is just going to be 1 over root u. Yeah, du. So think of that as like u to the -1/2 for integration purposes. And you get -1/2 times 2u to the 1/2. And then probably, to get everybody on the same page, just convert this back into x. So we have those cancel. We have negative square root of u is 4 minus x squared plus 3 arcsine of x over 2. We didn't do a plus c because this is a definite integral. And yeah, we could keep it in terms of u, but then we'd have to do 2 separate integrals, or 2 separate and then we'd have to change the bounds to fit u, whereas over here we're keeping it in terms of x. So rather than have one integral in terms of u and the other one in terms of x, I think it's probably better to just have everything in terms of x for when we go and evaluate this. So when we go and do that, now we should be able to do that without. This is backwards unit circle. So plug in 1 and you get negative root 3. This is going to be yucky. Plug in 1, you get arc sine of a half. What angle makes arc sine be a half? Is it pi over 6? Yes, it is pi over 6. So think about your unit circle. When arc sine is a half, that's when your y-coordinate is 1/2. That's the angle pi over 6. So arc sine of 1/2 is pi over 6 times 3 gives us pi over 2. Camera, thank you. Yeah, that's bad. I've been off on the camera all day. So pi over 6 times 3. Say again?
Oh, okay.
Right. So the arc sine of 1/2 is pi over 6 times the 3 out front gives us the pi over 2. So that's for plugging in 1. Then we got to plug in 0 here because it's not just a polynomial. If you plug in 0, what do you get for the square root? We get negative 2. And what angle makes our sine function equal 0? Pi, but even better than that, 0. Because the range of arc sine doesn't extend out to pi. The range of arc sine is just from negative pi over 2 to pi over 2. So when you evaluate your arc sine, you're only going to get an angle over here. So arc sine of 0 is 0. It is for arc tangent. For arc cosine, it's from 0 to pi. Why? Because of the graphs of sine and cosine and how we have to restrict those graphs to make the inverse function work. That could maybe be a video later. I don't want to guess. We could get bogged down in there for like a while. So for the same reason, we don't want to. That could be its own video. We could get bogged down in there for like a good 20 minutes if we wanted to. Let's not go down that rabbit hole. So then we condense this down to something less yucky, and we get a positive 2 minus root 3 plus pi over 2. Positive 2 minus root 3 plus pi over 2.
Oh, we don't have to like.
And that's it.
Oh, we.
That's it. I mean, well, how are you going to simplify that?
I was thinking we could do, like make the denominators the same and then do like 4.
Yeah, I mean, you could make it all one fraction, have 4 minus 2 root 3 plus pi all over 2, but it's still not like you're combining things. You can't combine, like you have a whole number, one type of irrational number, and then a completely different kind of irrational number. These don't play nice together. They just kind of look like that. If you want to do anything with it, make it a decimal.
Wait, is that constant? Is it minus negative 2? Oh, it's
That's an equal sign. Sorry. That's not a very good equal sign. Is that better?
Yeah.
All right. So this has like 3 things going on. It's got a U substitution going on. It's got your arc sine pattern going on. And then before that, it's got this trick of breaking apart the integral into 2 separate integrals using just your rules of adding fractions. Any questions or follow up on example 2? And did somebody put in the chat, hey, move the camera, and then I ignored that? Yep. Sorry, Kirsten. All right. Oh, yeah, I'm missing a DX.
That's pretty important. I know.
That's you can't get away without a DX. So lame board point. I'll come back and get that later. All right. This thing. Initial thoughts. What do you think maybe you want to do here? So, using the arc sine. What? Now, arc sine fits the bottom, sort of, if we do what to the bottom? Oh, so, yeah. So, how can you reimagine x to the 6th? If this is going to be arc sine, x to the 3rd squared. Now, why would we want to do that?
Because U squared and then U is X.
Yeah, so this is, if you think arc sine, and if you see square root of constant minus x to the some power, especially if it's an even power, it's reasonable to think maybe it's worth investigating arcsine. And remember, your arcsine pattern is du over the square root of a squared minus u squared. If we let u be x to the third, so that u squared is x to the third squared, and then a is just 4. And then what's the derivative of u? 3x squared. Hey, we have an x squared thing there. So that's how that works. So Ison's initial thought of maybe that's arcsine. That's right on. You might think, oh, it's just a u substitution, but u substitution is not going to work nice because if you just did a straight u substitution and said u is 16 minus x to the 6th, then du is negative 6x to the 5, and you don't have an x to the 5 up here, you only have an x squared, so that's not going to work. So a straight u sub isn't going to work out so nice here, actually, unless this is an x to the 5th. It's not, it's only x squared, but if you finagle this and say, yeah, let's kind of try to fit the u substitution pattern with arcsine, then it does work. So we can say this is 16 minus u squared, and if we let u equal x cubed, then du equals 3x squared dx, and we're just missing a 3 here to fit that pattern. And that's an easy fix. Just multiply 3 to the third. All right? So once we then go and do that u substitution, we'll have 16 minus u squared on the bottom, du up top. And then what does this look like when you integrate? To the arcsine. Yep. So x cubed is u, and a is 4. So you say for arcsine we have u is x cubed, and a is 4. And don't forget the plus c because this is just an indefinite. So this is another trick of taking an x to some power and rewriting it as kind of x to some power squared, or could be to some other power. There might be a situation where it's useful to have this as like x squared to the third power instead. But that's another one of those tricks that we're going to use because we want to see how can we get our u, whatever our u is going to be, du then would need to be something involving an x squared. Any questions with that? Example 3. All right, example 4. Initial thoughts? Well, let's try arctangent. So what's our pattern for arctangent? We have 1 over a, so this is 1 over a squared plus u squared, and then what's on the end? Du. So the du is going to what makes things not work so nice here. So that equals arctangent of u over a plus c. So could u be x? Let's try it. So if u is x, then du is dx, and if we substitute, now we have the integral of 1, the 1 plus du du. But that hasn't really done anything. It's still the same thing. Just swapped out this is a straight swap u for x, or u for x. So.
But then you must have the same integration.
So we're gonna end up in the same place. We just changed what the variable looks like. What are you saying? Yeah. I think if we had e to the x squared, that could work. That is not x squared. We haven't tried u equal 1 plus e to the x. Is there a reason why we don't try that? Yeah, we don't have an e to the x. So what if we just added that in there? So what are we? You could do that, or instead of multiplying, you could add, right?
You have to add it.
Yeah. So that's another trick. We can multiply and divide. With a constant, you can multiply and divide on the inside and the outside, and that's easy. You can also multiply and divide on the inside if you're involving a variable. So let's try that. So let's say, well, I need an e to the x. So let's get an e to the x, and then we have e to the x over e to the x quantity 1 plus e to the x dx. Right? So we're multiplying and dividing by e to the x. So we're multiplying by 1. Your brains hurt? Cool.
You multiply.
And then you could multiply at the bottom. You have e to the x over e to the x plus e to the 2x. Now, if we do that, we're getting away from doing our u substitution.
So we can what? So use
Yes.
one plus
Remember the thing where it was like,
So let's come back here and do our u substitution. So we have e to the x dx is du. 1 plus e to the x is u. Then we have this extra e to the x. Can we come back up here and yes, we could say, you know, e to the x is the same as u minus 1. And then put that here for this u. Say this is integral of du of u minus 1 times u. Now, don't get yourself too committed to this thing.
What do you think?
It's not wrong. This will take you somewhere useful
What?
if you know partial fractions.
I don't think I know that.
You don't know partial fractions
let's learn it.
because that's a BC thing.
Let's learn it.
No.
You
Okay.
guys
I don't know. Okay.
So instead, we're going to do, somebody else suggested, I think it was Michaela suggested something similar, but instead of multiplying and dividing, is the add and subtract trick. Somebody other than me said it. Now, no, before we do,
That was the question.
yeah. So we could multiply and divide by e to the x, and that takes us somewhere useful only if you have partial fractions in your toolkit. You don't. Partial fractions are, how do you take this thing and break it up into two fractions being added together?
Can we learn it?
Oh, yeah,
Can we learn
that
about
could be
that?
something, yeah, we could multiply this through, it doesn't help. That actually leaves us, that gets less useful. So instead of teaching you guys partial fractions, I'm gonna now back up and say, all right, that leads us to what is for us a dead end. Let's try something different. Do I know how to do partial fractions? I had to reconstruct it yesterday as I was doing this example. Say, what if I did that? Could I think, well, let's see if I can remember how partial fractions work. And I refigured it out for myself. And I was very pleased with myself. And I said, I'm not teaching that. So instead of multiply and divide, no, we like this u substitution. So we're going to say, 1 plus e to the x is our u. And so then du is e to the x dx. All right. So what now we're going to do is we're going to go back into this function, and instead of multiplying and dividing by e to the x, we're going to add and subtract that to the numerator. So we're going to say 1 plus e to the x minus e to the x. Because just like multiplying and dividing by the same thing as multiplying by 1, that's totally fine. Adding and subtracting the same thing is totally fine. You're just adding 0. And then, once we've done that, we separate two fractions.
1 minus e to the x.
Yeah. So we have 1 plus e to the x over 1 plus e to the x minus e to the x over 1 plus e to the x.
Oh, and then you use the.
And then you say, hey, this guy hits the second integral perfectly, and this first guy is super easy because that's just 1. So that integral is just x. This thing, you can now do that u sub straight, and you have integral of 1 over u to u. That's natural log of u. And u is 1 plus e to the x. And that's a hell of a lot easier than partial fractions would have been, I can tell you that. So this is why I'm not going to waste time
showing you partial fractions. It's useful to have that ability. So again, that's maybe one of those like after the AP test, I want to show you 3 things. I want to well 2 things for sure, maybe the 3rd thing. Integration by parts, matrices, which has nothing to do with calculus, but you need to see before you go into a STEM field in college, so that you don't have like just shock of what the hell are these things, and maybe partial fractions.
This is sad. So like when you separate the numerator, you get plus or minus, when you separate the denominator,
Yeah. So you have like 2 separate fractions, and you can have the same denominator, because common
they do
denominators.
have to have.
But then you eventually want them to not have the same denominator. So you want to turn one fraction that's like 1 over u minus 1 into something over u plus something else over u minus 1.
Why would you multiply?
Because you're trying to turn it into something like this, actually. Well, normally, yeah. So we have to figure out what are these somethings to make it work. That's why they're called partial fractions. So this is a part of that fraction. This is another part of that fraction. How do these add together to give you this thing? So it's a little ugly. We're not going to go down. There's another rabbit trail. We could spend another 20 minutes down that
So
rabbit
it's
trail.
like when you instead of multiplying by -1,
Yeah.
and then the top has to also multiply by -1. So then you have to find something where that times that equals 1.
Exactly. So you've got the basic idea of it. It kind of leads you into systems of equations,
Yay! I love.
We love that.
and everybody loves those,
That was
They're
good.
so.
which is what matrices are all about, actually. So
The system of equations is so easy.
It sounds like this
Where you have,
information
like,
could
the
help us on the AP
equations
test.
Um,
We should do it.
And elimination is always easier.
no, because again, that thing was easier than partial fractions would have been. So what we ended up doing with example 4 was a more efficient method than what we were heading towards with the multiplying divide. I missed a spot.
You missed a couple
I'm
spots.
sorry.
Oh, I guess that's okay. You should
You're
just
like
show
me
us-
talking to my kids when they're cleaning. No, go back and clean the floor some more, kid. All right, example 5.
Aren't they like 3?
Yep.
Why do you like 3?
Eleanor's almost 7.
That's old enough to. Yeah. I really think you should be. Oh.
It's an eventual goal. We'll get there. They need to be able to like reach the stove. So far, they can only reach the stove to like burn themselves. So it's better stay away from the stove.
You
I
sub.
feel like myself.
Not you sub.
All right. Example 5, the probably last thing for today. You look at that, and maybe you like throw up in your mouth a little bit because that looks yucky. But then once you've gotten over that, what's a guess?
You sub.
You sub. Throw up again. So we could try a U sub. Now, yeah, almost certainly this is a U sub. The trick is figuring out what should your U be, because you have at least like 2 reasonable possibilities, maybe 3 or 4.
You can't derive that line.
No, we haven't talked about how do you integrate the natural log of sine. We don't know that. So since we don't know how to integrate the natural log of anything,
So is ln of sin x.
maybe we should make the U natural log of sine x, so that we can get rid of the natural log from in the integral. Yeah, that's a good idea. Then du,
Where it's like
how do you integrate? How do you differentiate natural log?
1 over
Not
sine
quite.
x.
So not 1 over sine x.
Sine over x. Okay.
X over x.
Yeah.
So u over u.
Yeah, u over u prime. So what's the derivative of the inside? Cosine over sine x. So remember, so that now you got to remember not just your integration rules, you also got to remember your differentiation
That's
rules,
cotangent.
and that's cotangent.
It works out.
And then it works out beautifully. So you say,
How good
there's
that
my
is.
u, because Noel's pointing out we don't know how to integrate the natural log. So let's try to hide that inside our u. That's a good reasoning.
Like, because you might think, oh, the really inside thing is sine x, so let's have u be sine x. But then you have to deal with the natural log of u, and you don't know how to integrate that. So hide the natural log, which you don't know how to deal with, inside of u. And then remember, differentiation rules for log is the derivative of the inside over the inside. And then remember your trig, hey, cosine over sine is cotangent. And then that turns out to be integral of u to u. And that turns out to be really easy. Yeah.
Why? Because you use ln sine x.
So ln of sine x is u. And then cotangent x dx is du. Yeah. And then just remember, it's not about you. So put the natural log back in. You have natural log of sine x squared plus c. Ta-da. So 8.1 is just kind of greatest hits of integration. That's basically what this is. All these little tricks that you can use, multiply and divide, or add and subtract the same thing, or break apart a fraction so that one thing's a u substitution and another thing's an inverse trig. Or, hey, I don't know, I don't like this look of the ln, so hide it inside of a u substitution. You have homework, it's due tomorrow, 8.1a. If you want to jump ahead on 8.1b, you can keep working on that as well. We've got example 6 and 7 to look at tomorrow in addition to going over the homework. And that's it. Although you might run into something also that is like, well, actually, we just don't know how to do this. So we'll look at what that looks like tomorrow with example 7, where again, we have like 3 integrals that all look very similar, and 2 of them we can do and 1 of them we can't. So I'll see you guys tomorrow.
Actually, I just wonder about the situation. Can you go through that? Is that going to actually take you time?